So, like we said, even if a drug is not in a solution form initially, ultimately when it breaks down, it will become a solution. Drug molecules are classified as either electrolytes or non-electrolytes, depending on whether or not they form ions in solution. So, non-electrolytes will not form ions in solution, while electrolytes will form ions in solution. Some examples of non-electrolytes would be alcohol, propylene glycol, and glycerin, and you may recognize these because they're also co-solvents. So based on the degree of ionization, electrolytes are going to either be split into weak electrolytes, which are composed of weak acids and weak bases. These weak electrolytes are going to partially ionize in solution, and strong electrolytes are going to completely ionize in solution. And this means that their end products would just be the ions that they form. For example, strong acids such as hydrochloric acid, and then strong bases such as sodium hydroxide, and all salts such as sodium chloride. So most drugs are going to be either weak acids or weak bases, so they're going to be weak electrolytes. For example, phenobarbital is weakly acidic, while morphine is weakly basic. Next, we're going to talk about ephedrine. Now, ephedrine is a weak base, but treating it with a strong acid will make it into a salt. So treating ephedrine with sulfuric acid will give us ephedrine sulfate, while treating ephedrine with hydrochloric acid is going to give us ephedrine chloride. And now these two products are going to be completely ionized in solution because they will be salts. In aqueous solution, sodium acetate will completely ionize because it is a salt of acetate, and this is just one of the clicker questions. The acid-base behavior of a drug will affect the drug solubility, the chemical stability, and the pharmaceutical activity of the drug. So now we're going to talk about some concentration terms that are used. The first one being moles. Moles is just the weight of the drug in grams divided by the molecular weight. And millimoles is just going to be the moles times 1,000. So one of the questions in our clickers was to calculate the millimoles contained in 5.55 grams of calcium chloride with a molecular weight of 111. So I just worked that out for you guys. It's just going to be 5.55 divided by 111 times 1000, which is going to give us 50 millimoles. So osmoles or milliosmoles are also quantities, just like moles and milliosmoles. Moles and millimoles. So a mole is going to represent the molecules, while the osmoles are going to represent the number of particles that each molecule contributes to a solution. So if we had 1 mole of sodium chloride is going to completely ionize into 1 sodium ion and 1 chloride ion, as you can see right here. And so that's going to give us 2 particles, and those particles are going to be the Van Hoff factor I, or basically the number of particles that each molecule contributes to a solution. So in another example, the Van Hoff factor of glucose is actually going to equal 1, and this is because glucose does not ionize. So as a general rule, non-electrolytes are going to have a Van Hoff factor of 1, and this is because non-electrolytes do not ionize, and so their Van Hoff factor is going to equal 1. And for strong electrolytes, it really depends on the number of particles that they dissociate into. So sodium chloride would be 2, sodium sulfate would also be 2, and then the rest. To calculate the osmoles, this is going to be the number of moles times that Van Hoff factor. So to calculate the milliosmoles of this problem, we can see that calcium chloride is going to dissociate into one calcium ion and two chloride ions, and so the particles that it contributes to the solution is going to be 3, 1 plus 2. So the milliosmoles is going to be the number of moles times that Van Hoff factor times 1000. So it's going to give us 150 milliosmoles. An equivalent is an expression used to address the number of charges, positive or negative, that a molecule contributes to a solution. So the equivalent is just going to be the moles times Q, and Q is going to be the absolute value of one of the ions that dissociates in the solution. So for example, calcium chloride is going to dissociate into one calcium ion with a charge of 2 plus and two chloride ions with a charge of negative 1, and so it's going to be the absolute value of one of those ions. So either way it's going to be 2. So the absolute value of 2 plus is just 2, and then 2 times negative 1 is going to be negative 2, but the absolute value of negative 2 is just going to be 2. So to calculate the milli equivalents, we're just going to take the number of moles times Q times 1000, and that is going to give us 100. When we express the strengths of pharmaceutical preparations, we can either use weight in volume, volume in volume, or weight in weight. And the numerator, or the top number, is going to be the API, or the active ingredient, while the denominator, the bottom number, is going to be the entire solution. So some examples of that would be isopropyl alcohol. This is going to be volume in volume. Then hydrocortisone cream is going to be weight in weight, while chlorhexidine is going to be weight in volume. To convert weight by weight to weight by volume, we're going to notice specific gravity, and here it gives you that equation. And again, we can rearrange the equation to also find the weight by weight of the solution as well. And then just vice versa for converting volume by volume into weight by volume. And here's the equation for that. So to solve this problem, it's going to be percent weight by volume is equal to percent weight by weight times the specific gravity. So plugging in all those numbers to get percent weight by weight, we're just going to divide each side by the specific gravity, 1.3, and that's going to give us 65.4%, which is going to be the weight by weight. And then for this problem, we're not going to need to rearrange the formula at all. We're just going to plug in those numbers and get 27.6%. So next we're going to talk about molarity and molality. So molarity is going to be the moles of solute divided by the volumes in liter of solution. And then molality is moles of solute divided by weight in kilograms of solvent. So to solve this problem, they give us 7% by weight. They also give us density. They give us the molecular weight of glycerin, and they want us to find the molality. And so remember that 7% by weight means that there's going to be 7 grams of glycerin over 100 grams of total solution if the density of the solution were equal to 1. Now the problem is that the density is not equal to 1. It's actually 1.0149. And so to find the mass, the actual mass of glycerin, we're going to take 7 grams times the density. And that's going to give us the actual mass of glycerin. So to find the moles, we're just going to divide the actual mass of glycerin divided by the molecular weight of glycerin, and we're going to get 0.0771 moles. And remember, the molarity is just going to be the number of moles divided by the liters of solution. So we can just assume that the liters of solution is going to be 100 milliliters, or 0.1 liters. So dividing all that together, we're going to get the molarity equal to 0.771. Now this is just the same problem except they're asking for molality this time. And so from the previous problem that we just did, we already know the moles of glycerin is equal to 0.0771 and the mass of glycerin is going to be 7.1043 grams, and molality is going to equal moles divided by kilograms of solvent. So we already know the moles, and so now we just need to find the kilograms of solvent. And once again, to reiterate, that 7% by weight is just going to be 7 grams of glycerin over 100 grams of solution in total, and this is only if the density is equal to 1. So to find the actual kilograms of solvent, what we're going to do is we're going to take that theoretical total mass, 100 grams, and we're going to subtract the actual mass of the glycerin and get 92.89 grams. And so this is the mass. This is the mass of solvent if the density were equal to 1, but the density is not equal to 1, so we're going to have to multiply that by the density, giving us 94.274 grams, and this is going to be the grams of solvent. And so remember, molality is just going to be moles divided by kilograms of solvent. So dividing all of this out, we're going to get 0.817. And that is the end of this lecture. I'll see you guys next time.